Welcome to the Kuwait Foundation for the Advancement of Sciences. We are very pleased to have you here in this speaker series of KFAS Links. I would like to introduce you first to the Director General of KFAS, Dr. Adnan Shihabuddin.
مساء الخير جميعا. Good evening everybody. راح أتكلم باللغة الإنجليزية لأن في بعض الحضور أعتقد خصوصا ضيوف جايين من برا فاسمحوا لي أتكلم باللغة الإنجليزية. I welcome all of you to the KFAS Links. As Yusuf said, KFAS Links is a monthly speaker series where KFAS hosts prominent subject matter experts to enlighten us with the aim to promote science and technology in Kuwait. And we are very proud this month to be hosting eminent Professor Omar Yaghi, the director of the Berkeley Global Science Institute at the University of California in Berkeley. And of course, I take special interest in that because I studied in Berkeley centuries ago. Professor Yaghi is the winner of the prestigious Albert Einstein Award of Science. And I'm proud to announce, because it's no longer a secret, it's been approved, he is the winner of the Kuwait most notable annual award in science, the Kuwait Award. He will be awarded by His Highness, among others, in December 13th. Congratulations. Professor Yaghi, before I go into the introduction, when I saw the citation of the evaluation committee about why he was awarded the Kuwait Prize, I was stunned. I don't know, the numbers appeared hundreds of thousands of citations per year or something like that. I think Dr. Nouri Al-Awadi is behind. She was coordinating that. Remember my reaction? So, I mean, I haven't seen anything like that in terms of citations. So, it's clearly Professor Yaghi has accomplished a lot, but he is the inventor of a new metal organic framework, highly porous structures for storing out liquids and gases for many applications. And he will talk about it, so I'm not going to preempt him. But just let me say that over modern humankind, every now and then there is an invention that ends up having a very important impact. And with great magnitude, that impact significantly changes the way we live. And we believe, based on what I've read, and maybe tonight you will tell us, and maybe you will tell whether it is true or not, this may be one of those inventions that changes a lot about the way we live. I hope so. According to the United Nations, an estimated 42,000 people die every week from diseases related to low water quality and an absence of adequate sanitation. Now, the possibility of producing fresh water in worthwhile quantities and in affordable and sustainable methods can not only help to significantly reduce world dehydration, but also present amazing opportunities for agriculture and the environment. And tonight, we will learn about one out of hundreds of potential applications of this new material, which is the title of the talk, How to Harvest Water from the Atmosphere. So I'm proud to introduce to you Professor Omar Yaghi to give you the lecture. I'm not going to run through his CV. It's available on the website. It suffices to say that he is, I think you got your PhD from Urbana, right? But more importantly, you work in Berkeley now. Please.
Thank you very much, Dr. Adnan, for that kind introduction. And thank you all for welcoming me here, for your generosity, your hospitality. And I'm very happy to be here. This is my first official visit to Kuwait and to, of course, KFAS. And I want to share with you some of our work on water harvesting from air. This is an application that emerged not because when I started doing research, I aimed for it. And just like all basic research, I started with an idea trying to solve an intellectual problem, and it has led to the discovery of the largest classes of materials ever known, and also to numerous applications, as I will show at least some of them tonight. But there is a journey behind these materials and this discovery. So I want to take you through my journey, and in the middle we can talk about water harvesting. But I hope that you find it useful on how we were able to discover these materials and what is behind that discovery. Just a word or two about where I am from. I'm originally I was born in Amman, Jordan. And Jordan, as you can see on the map, is not very much bigger than Kuwait. Okay, we're very small countries, but we are very peaceful countries. And I left Jordan when I was 15. In fact, I was thrown out of the country by my father, who said, I think it's time for you to leave. Maybe I was showing teenage tendencies. But before that, I came out of our house to take a photo with my younger brothers. And I come from a family of, we are a refugee family, and I come from a family of 10. And I noticed that I'm holding a book here. Okay, that tells you a lot about me as a child. I didn't play with the other kids. I just stayed and studied all the time, did my work. And then when there was no more homework, I either read, and if I got too tired of that, I was asked to take the rocks from the garden and make a pile of them. As you can see there is a pile of rocks. That was sort of one of the chores that I was involved in. But another thing was that in those days, and I think is still true today, that water came in from the city to our house either once a week and sometimes once every 2 weeks. And sometimes it was my job to be there at dawn to turn the faucet on or turn the pipe on so that the water goes into the tanks, fil khazanat. Okay, so that we have enough water for the rest of the week until it came back again. The reason you have to wake up early is because you want to catch the water, the first drops of water, so that you can fill all the tanks. Because by 1 o'clock or 2 o'clock, it stopped. So, I call that water at dawn. Okay, I had to wait for it, and I've always liked looking at the map and wondering, as a child, whether other people in other countries like the U.S. or Russia wait for the water at dawn. So this is just something that I remember in the context of today. But you might think that my life as a child was miserable, but it wasn't. There was a lot of things that happened. Needless to say, the love of the parents is always important. But also another break came in my life when I was a child. It's like in Hollywood, the actors, they have a break. Well, this was my break. I saw these models like this in the library, in one of the books that I happened to come across. And they just captivated me. I was a young child. I didn't know what they were. Later, I learned that they were molecules, and I was in love with them from the very beginning. I was also in love with crystals, and for those of us who do organic chemistry, you will always have a lab in organic chemistry where you make organic crystals of organic compounds. And it's quite spectacular. You take two solutions and clear solutions, you mix them together, and out comes things that look like snow falling. And those are, if you look closely, those are crystals that look like this. So that's the beauty, not just of the models, but just the beautiful crystals captivated me. And when I was a graduate student, I discovered something that was truly unusual, and I wish we had another hour because I'll tell you about how I came about this discovery. But for now, I would say it's suffice to say that this is a molecule that there is nothing like it. There has been nothing like it, and after I discovered it, there has been nothing like it also. This is really a unique example of an inorganic, this is a vanadium oxide, that looks like a rice ball. And I discovered not just that it structures like a rice ball, which was unique, but also that it seeks other molecules that have a cyanide ending on them, like acetonitrile. And the acetonitrile, the cyanide fits directly into this ball. So again, a very beautiful, beautiful compound. So when I got my independent position, the fun is over. You have to now think of a real problem. Okay, you have to pay the bill. You have to find a way to pay the bills. You have to start a lab. You're supervising students. So now you are mixing the fun of doing the science with the not so much fun of the business of running the science and making sure there's enough money to support the students. So I always felt that societal problems can be solved by new materials, because new materials allow us to have a different platform from which we can solve. It can change the equation for us. And so I aimed for new materials. And the way one can craft this not so intellectual objective is that if you think about the sort of materials that have been very useful in humanity, you won't come up with too many. And the striking thing, they're either organic or inorganic, but never mixed organic, inorganic, okay? I'm sure that many of you now are making a mental list of the most important materials known and useful in humanity. So let me show you my list and see how that matches yours. Without alloy, we will have no transportation. Okay, so this is a very useful, it's inorganic, it's metal-based. Without zeolites, we won't have petroleum, because every drop of gasoline goes through a zeolite to make gasoline. Refined gasoline, that's inorganic. Originally it's a mineral, it's a silicate mineral, but Union Carbide back in the 30s was successful in making it in the lab, and now it's shipped to oil companies in multi-ton quantities every week. Concrete and steel, okay? And you can see this in every country that is doing very well. There are buildings that are going up and up and up towards the sky. And without concrete and steel, we wouldn't be able to tell the world how successful we are and modernize our society. So you have, that's inorganic. Silicon, okay, computing and everything that comes with it, internet and so on, that's inorganic. And glass is inorganic. It's an important material. We don't think much about it, but it is inorganic. And plastics. Okay, plastics allow us to have things that are affordable and also package them for safety and easy manipulation. Those are organic, and then of course drugs, they're organic. So that's it. I can't come up with others that really fit in this class of great materials. You might, maybe nuclei, but in terms of man-made materials, these are so none of them is metal organic. And so the idea is, what happens when you combine organic, the softness of organic, and the ability to manipulate organic chemically with inorganic, which is robust and sturdy. So that's really the question ultimately that I articulated, how to make useful materials by combining inorganic and organic building blocks. Now, when I started out 26 years ago, my own research, the way people made materials was, we used to joke, this is shake and bake, we used to call it, or mix and wait, or mix and match and things like this. And that's just a statement about how unpredictable the synthesis of materials was. You mix stuff together, and I did it as a student, mix stuff together and you heated it up and you got the thermodynamically stable product, and you were at the mercy of what nature gives you, which is fine. I like to be at the mercy of what nature gives me, but really to make a big difference, you need to be able to control matter on the atomic and molecular level. And that was really the thing that interested me. So, metal organic, you know about metal complexes. Okay, they're known, they've been known for a long time, over 100 years. Okay, and some of them, like this one, is known to have little crevices into which guest molecules can go in. Okay, and this is now I'm beginning to talk about the subject of my research, where you're trapping things. And so the problem here is that if this guest left, the material broke down because they're not connected to each other. The framework or the house is not connected. And so they broke down. There were things that were connected. The metal here is in blue and the organic is in gray. And so you can see very clearly in this structure, you've got metals that are connected, single metal atoms, to make what looks like a framework. When I saw this, it was truly inspiring. And so, as an assistant professor, one of the things that I started doing was making things that look like this. And very quickly, we discovered that they collapsed. Okay? They collapsed when you remove the stuff that's inside. When you make the material, there is solvent and other molecules trapped. You take them out so that you can make a porous material. When we took them out, they collapsed. So they were architecturally unstable, or they were too frail. And they were not designable. They were not designable because people who work on metals know this very well, is that a metal can have, in that case, copper 1. It could be have 4 connections to it or 3 connections. And it's not quite predictable. So we couldn't predict really the structure. And they are not chemically stable because the bonds are weak bonds. A copper-nitrogen bond, which is from a neutral ligand, is a weak bond. So the stage is set for us to address this problem. It would be great, like zeolite chemists, was a dream for many, many years, 80 years, to make metal organic porous materials so that you can functionalize the organic, craft the interior, vary the inorganic from among the metals in the periodic table. And they know, the zeolite chemists, petroleum chemists, they know very well the power of the metals as catalysts. So I was trained as an inorganic chemist, and I knew that chelation, what is called chelation, like a carboxylate, chelates metals. It assembles metals together. And so what we did in this, we took an organic unit that has 2 carboxylates on it, and that hold, in this case, zinc atom, can also hold copper atoms, and link it up to another one. And we worked very hard at crystallizing this. These were not easy to crystallize in the beginning, but we've worked out a cocktail of conditions that is still used today to crystallize these materials. People said you can't crystallize them when we proposed this, but we were able to crystallize them. Again, I would need another hour to go over the professor-student interaction that yielded the conditions under which these crystallize. So now you made a metal organic framework. It's a framework made now of a clustering of metal, not a single metal ion as we had in the other structure I showed you, the frail structure. Now you have a cluster that is linked together by an organic, and it's repeating. It's like a grid. And then these molecules in the pore are what's called DMF, dimethylformamide molecules. that fit the pore. And then the question was, when you remove those DMF molecules, will the structure be more stable because of the chelation of the carboxylate, or will it collapse? That was really a big question in the field. I still have the reviews of this paper to show my students about the challenge that we were facing in those days. But it's very clear that for the physical chemists in the audience, this is the gold standard for measuring porosity, where you measure the uptake of gases at 77 Kelvin. And from this uptake, you can obtain the surface area and pore volume. The shape of how gases go in and saturate the pores at low pressure tells you that this material is permanently porous. If it was not permanently porous, if it had to deform or pop open, the shape of that isotherm will be different. So I think the message here is that we were the first to figure out a way to make these materials architecturally stable, and the first to measure their gas uptake so that to prove beyond any doubt that they are permanently porous. The reason I emphasize this is because in those days, when I was a young assistant professor, I would give lectures like this in conferences, and everybody stands up and they say, these will never be stable, they would never be porous, and things like this. And so it was very, very important to give legitimacy to these materials from the outset and do this hard experiment. So they are permanently porous. And of course, if you look at the crystal structure of this, you can relate it to the square grid. Okay, if I take the carboxylate atoms of the carbon in the carboxylate, I connect them, I get what's called a square grid, or the 4 to the 4 pattern that you see here, which is exactly the pattern that is in KFAS building. If you go in the foyer and you look up, that's the pattern. You see it here in dark metal. Okay, that's the exact pattern. And if there's anything you're going to take out of my lecture, you will take the following. Any structure you can imagine, any pattern you can imagine, can be made in a MOF now. Okay, and that's really what has changed a lot of things for chemists and for scholars interested in chemistry. So here's another pattern. This is the primitive cubic Escher drawing. Now, unlike the square grid where things are connected in 4s, here they're connected in 6s. You see 6 spokes coming out of this vertex. So I'm going to design something based on this structure. And for that, we took the main component of plastic, which is terephthalate. People who work in the petroleum industry know that these are very cheap components of byproduct in petroleum chemistry. And we took zinc oxide, which is the main component of sunscreen. This zinc oxide is the one that's going to give me 6 condition. But notice that it's a cluster of metals, so that I can make a nice, robust joints that then are linked by organic. And then, of course, it gave us what we call MOF5. Now, I didn't say anything about the square grid. The square grid, although that was really the beginning of the revolution, people paid absolutely no attention to it because the surface area of that structure was 275 meters square per gram. And zeolites were double that. So nobody paid any attention. But when we made this compound, we call MOF5, and it has zinc oxide and linked by organic. The yellow ball, by the way, is the space that is encompassed by the material into which you can put carbon dioxide or other molecules. But these are the beautiful crystals that we were able to make and analyze by X-ray crystallography to figure out the connectivity. So people paid attention to this because when we measured the isotherm, as you can see here in red, we were able to determine that 60%, experimentally, 60% of those crystals were open space. Okay, now we can make MOFs that are 90% of the crystal is open space. And the surface area is 2,900 meters square per gram. So that was a new record in porosity. No one has measured anything beyond 1,000 for a non-crystalline material like carbon. Zeolites, 600 meters square per gram. Mesoporous materials, about 1,000 or 1,200 meters square per gram. So 2,900 meters square per gram was breaking the record by far. So we were very excited about that. So now you have a material, you have a way of making these materials from organic and inorganic. Immediately as a chemist, we realized that the importance of this discovery, and that is that now I can take the organic and modify it. Put a functionality there. If I put a functionality here, then my interior is chemically modified. And I could also expand it. But notice, without changing that original, let's say, topology or connectivity. Any other material, any other solid state material, once you do what I just described, it will break apart or it would change its structure, and therefore you can't design it, you can't use it. So we functionalize the pores so that you can have different environment, hydrophobic, hydrophilic, and we can expand the pores. And we've expanded these so much that you can even put proteins in there, not just small molecules. So, okay, so the stage has been set, and we, the student who discovered MOF5 said, "Professor, I don't think we should report the synthesis exactly how we did it, otherwise we will create many competitors that will jump on the area." And I said, "No, we have to report it exactly as we did it, and in fact report it in such a detail that a high school student can repeat it." And we did that, and that was the not just ethical thing to do, but also smart thing to do, is that we taught the world how to make MOFs. And so we reported this, and some of these, and the world reported a lot of these. We reported these. These are the linkers, organic linkers, struts that one can use. I mean, nobody has imagined that you can make a material out of things as long as this. So these we call ditopic because they link along two sides. But you could also have tritopic of various compositions and various atoms. Tetratopic that link up along four. More tetratopic, anything you can think of could be used. Further tetratopic, chiral also. Okay. Pentatopic. Okay, hexatopic. Okay. All of these have been made. This is only a cross section of the linkers that have been used to make MOFs. Octatopic. Dodecatopic. Okay, it works. The chemistry works. And it works in many different contexts. And many different metals could be used. Many different clusters could be used. Discrete clusters like these, but also extended clusters. So the field was born. And this is an example. This is the epitome of a MOF. Everything why do they have high surface area? We went in there and determined where the gases are located and where they're sitting to tell us about the surface area that they're covering. And we found that everything you're looking at is a adsorptive site. The metal oxide units, the edges of the six-membered rings, and the faces. And that's why this material has 10,300 meters square per gram. Okay, 10,000 meters square per gram. Okay, that's about the size of a US coin, US dollar coin. And so let me just tell you, this is so porous that if you take that gram and you unravel it to the atomic level, to the molecules that we've assembled it from, it will cover an entire football field or a soccer field. Okay? So you can see here that the original discovery, MOF5, beat the 1,000-year record held by carbon, which was discovered by the Chinese, and the mesoporous minerals and zeolites. And so 5 years thereafter came the French with a material they call Mil 100. That's another MOF, just based on the same chemistry I just showed you. And their surface area couldn't beat ours. Then we reactivated MOF 5. We were learning how to remove all the things in the MOF, in MOF 5, and to measure its optimal surface area. And we beat our record. And then we made MOF 177. When we made MOF 177, it beat the record of MOF 5. And it was so high that we thought there's nothing going to be more porous than that. We called it the queen of MOFs. Okay, the queen of MOFs was it. But then the French came in and they beat us. Okay, then the Texans came in, they couldn't. We reactivated MOF 5, we couldn't beat the French. Then we made another material we call MOF 20 sulfur-based linker. We couldn't beat the record. But then MOF 177 was reactivated and re-examined, and we beat the French. This is MOF 5 optimal surface area. This came in from an assistant professor that I mentored at Michigan. And then the French, they couldn't beat our record. The English couldn't beat the record. The Michigan group again. This is our compound. We couldn't beat our previous record. Then Northwestern University came in. They beat everybody. And then here, we just by a little bit, we regained the record. Okay, so we've been having a lot of fun over the years. And then the Germans came in. They couldn't. And then the Nottingham group in England, they came back. They couldn't beat us. This is my student who's now professor in University of Pittsburgh, couldn't beat the record. The Germans couldn't beat the record. Now the record is held by Northwestern University, okay, which is fine. They've used the same kind of procedures that we used in terms of making the MOF and measuring the porosity. And so this is the optimal, or this is this surface area we call BET surface area, which is sort of one of the ways of expressing porosity, but this has the highest surface area. And then if you want to make anything higher than that, you have to really modify your linkers so that they're acetylene type of linkers rather than the phenylene type of linkers. Okay, so this is Dr. Rana Lane, who I met back when we were just discovering MOFs, and we were making a new MOF almost every week. And I was like a kid in a candy shop. I was making models out of them, displaying them on the screen and enjoying myself. And he came down from this water treatment company called Nalco in Chicago to see what is all this hullabaloo about with the materials. And so I gave him a lecture, for 20 minutes about all these wonderful, beautiful structures. And he said, at the end, what are they good for? And I thought, wow, I can't believe he would ask me such a question. I'm a scientist. I'm like an artist. I'm interested in beautiful things. I'm not interested in useful things, right? I'm a chemist. I'm a basic scientist. I'm supposed to be answering intellectual problems, not worrying about what society might need. This is the way we were taught in graduate school. Okay, so the old Germanic thinking. Well, he said, well, Omar, you can be an excellent professor doing what you're doing, but you'll never be a great professor unless you take these great materials and you use them to solve society's problems. And so that was an eye-opening experience, and it's a lesson for me because talking to people, sometimes they trigger something in your mind. And so the idea was that we have unmatched porosity. We have a diversity never seen anywhere in chemistry. We have a multivariability of the component. And we have a material where you're stitching things together through strong bonds to make robust materials that were riddled with holes. So the idea was, could we take large or gases that fill large space and compact them within the pores, just like bees coming onto a honeycomb. Let me just say that when we reported that high surface area, and this is another fateful meeting, my colleagues my friend at BASF recently said that at the time he thought the number was so unbelievably high that he thought it had to be a misprint. And so he was busying himself trying to scale up the synthesis we publish and to verify the surface area. And thankfully, he can verify it. In fact, his surface area was a little bit higher than ours. And since that time, about 16 years ago, I have been collaborating with BASF on the scale-up of MOFs. So now BASF is scaling MOFs. This is Ulrich Müller. We are scaling MOFs to multi-ton quantities with BASF. You can see here, this is a plant that produces MOFs. This is one of the MOFs being packed in a barrel. And you can see these are just powders. They're nice crystalline powders. And they can be shaped in many different forms for various applications like catalysis and gas storage. So in trying to address societal problems, it seems reasonable to start with gases because of the high surface area and the difficulty with which gases can be stored. So these are the gases we looked into. Hydrogen, because it's a very clean fuel. Methane is cleaner than petroleum. Carbon dioxide is bad for our planet, and water, we are in need of fresh water. So the idea then was you have a MOF here in red, and that these gases would assemble themselves onto the interior surface of the material, so that instead of the gas molecules being far away from each other as they normally are, repelling each other, now by virtue of their attraction to the MOF, they can come and be compacted next to each other. Exactly like bees on a honeycomb. And that was the idea. So how far have we gotten? I'm not going to go through all the technical stuff, but I'm just going to show you the product. This is an automobile, Mercedes demonstration model that is equipped with a MOF fuel tank that is a hydrogen fuel tank. And at room temperature, we can store 2% by weight hydrogen, okay, which is not the 5% that is required or 6% that's required by DOE yet. But at 2%, it's still appreciable amount that the automobile industry is very much interested in it. If you just do the experiment at 77 Kelvin, for example, to store hydrogen in chemical plants, stationary application, you can take a tank filled with MOF can store double the amount of hydrogen. Even though the MOF is taking space, volume into the tank, you still can store more hydrogen, double the amount, because the hydrogen is compacted in the pores. And that's where the excitement is. Now, the natural gas problem or the methane storage problem is solved because of MOFs. It used to be a problem, but now this automobile was equipped with a MOF fuel tank and driven all over the world, 28,000 kilometers. This was a test after we've done the laboratory discoveries and tests. BASF put the fuel tank, the MOF fuel tank, natural gas fuel tank, into this automobile, and German explorers took it all around the world, and it's being fueled from different locales, different temperatures, different trace impurities of the natural gas in the different locales. And at the end of this exercise, the MOF was tested and found that it only lost 10% of its porosity. But that meant that you can now go to the next stage, and the next stage was a fleet of automobile that now can triple the driving range. Okay, you can store in a tank filled with MOF, you can store 3 times the amount of natural gas than a tank that does not have the MOF. Same temperature, same pressure. And so this is something that is poised to be marketed. Right now, as long as I think that that petroleum just went up to $60 a barrel, and so this becomes viable. Okay. Carbon capture and conversion. The biggest problem with carbon capture is that you have to separate it from water, which is in the combustion gases. And so you need a way, and water goes into the MOF and sits exactly where carbon dioxide would. And so you can make a carbon dioxide loving material, but if you don't exclude water, it will replace CO2 and it becomes inefficient. We figured out a way, and I'll talk more about this later tomorrow in my lecture, but we figured out a way of incorporating organic moieties or primary amines to covalently bind CO2 and in the presence of water. So just to show you how well this works, this is, for the engineers in the audience, this is a breakthrough experiment where you take a bunch of MOF, put it in a container, and then expose it to a wave of gases, in this case CO2 and nitrogen in the presence of water and the absence of water. Here, the material was functionalized with methyl without water. You test it and it holds CO2 very well until the pores are filled, and then the CO2 breaks through. Now, if I introduce water into the mixture, you see the efficiency of the material goes down. Now, if I functionalize the material, the dry breakthrough is here, and if I introduce water, the breakthrough is not changed. That means the efficiency of the material is maintained, and that this material, when it's functional, when the pores are functionalized with the primary amines, they are selective to plucking out CO2 in the presence of water. This is a breakthrough experiment in many, many ways, and this has opened up the field of using solids to capture carbon dioxide in the presence of water. Not only can you convert carbon dioxide, can you capture, but you can also convert it to methanol, which is an important starting material. And here, the catalyst that everybody uses is enclosed in a MOF. Okay, so that now you can access all sides of the catalyst. And since the MOF is porous, you can control what gets in and what doesn't. And this is the activity of the MOF catalyst compared to the state of the art. This is the copper, zinc, alumina, and this is the MOF. Okay, that's the sort of thing that these materials they are changing not just the way we think about making materials, but the way we use them. Okay, now I want to come to the harvesting. So now you can see the making of the material and the preparation, the groundwork for doing this hard problem of taking water out of the atmosphere, low humidity atmosphere. Now, I need not tell you, but a significant part of the world lives in highly stressed water regions. So you probably already know this is a very, very large number, and it's not my salary. But it's how many liters of water are in the air at any one time. Okay, that's a lot of water that is not being really harnessed. There are 160 countries import their water. Somebody else is in control of it. And again, that's not just a question of watering regions, but it's a question of security. And 1/3 of the world population has no access to clean water. So water is probably the biggest problem facing us, facing humanity, aside from war. Water is a big, big problem. The amount of water in the atmosphere, just to give you an idea, is about as much as you have in lakes and rivers on our planet. So there's a lot of that, just another way of saying there's a lot of water that could be harvested. Well, look to nature. What does nature do? Nature, this beetle that lives in Namibia on the coast you get fog, not low humidity, fog, and this beetle has ridges on its back, nanoscopic ridges, that allow water to adhere to it and nucleate droplets. Okay, but that's high humidity. Of course, you're all familiar with the spider silk as a nucleation site for water. The cactus spines collecting water before they seep in. Those are all high humidity sources. Fog comes in, and this is a way to collect water, but we learned from that. There are clays that have water in them. The water in clays is stuck within the pores of the clay so tightly that you need to heat it up to 300 or 400 degrees C to remove the water. You couldn't use, although these could be used for low humidity, but you have to put in a lot of energy. So no way that this could be economical. You know about the fog capture with mesh, but here's a device. This is a very large unit that is based on clay-like material. And you can see here there's a wire, and this wire is to plug it into the electric. Okay, so this is, again, this is not economically viable, although some people are using this because they're desperate to have fresh water. So the dream is, could we use what in Star Wars Luke Skywalker does and make farms of some kind of material, maybe a moth, like the ones I showed you, that could trap water from the atmosphere and be useful in that way. Now, while we were studying CO2 and having to avoid the water and deal with the water, we were studying the uptake of water by moths. And then when the students showed me this, you can see here, just to give you an idea, 0.2 is about 20% humidity, relative humidity. That's what you can think about. This is 40%. But you can see that when this material is exposed to water, it takes up water at 20% humidity in red, okay? And then if you heat it up to 45 degrees, you can remove the water, okay? And it takes up 42% of its weight basically in water. So I looked at this and I thought, wow, that means I can take this water and put it in Tabuk at night, extracts the water from the atmosphere, temperature is low, humidity is high at night relative to day. During the day, temperature is high and low humidity, so the water comes out. That's what this plot is telling you. No energy input at all aside from sunlight onto the material. And that was really our realization that maybe you could use moths to make water, to drink water, to make drinking water. So here's the moth, and it operates. This is each peak is a cycle of uptake and release, uptake and release. And you can see the material is very stable, and it behaves beautifully. So we were on our way. We looked deeply into what is the water doing inside the moth, and found that this particular material has two kind of pores. There is a tetrahedral pores and an octahedral pore, but I don't want to describe these in detail, but only to say that water start aggregating, and in a very beautiful way, in cubes and highly symmetric form. And just like on the back of the beetle is inside the moth, except this is water from low humidity. So we demonstrate that in the lab. We had to demonstrate also outside. So we designed basically this device. You can think of it as a jar with a lid. On the inside of the lid, you have the moth. At night, you open the lid, water goes into the moth, and you close it in the morning before sunlight. Sunlight comes on. It hits the bottle, the jar. The inside of the jar heats up. The outside is room temperature. And it can heat up to 60, 70, 80 degrees, depending on where you are. 100 in Kuwait. That's better even. And then the water comes out of the moth, trapped into the jar. Now think about it. Outside, the humidity is 20% or 10%. Inside the jar, it's 100%. So you just need that temperature difference between the inside of the jar and outside the jar to get the condensation. Okay? And that's exactly what we were able to do here in this device. You can see that this is the part where the condensation occurs. I'm not sure if you can see all the way on the top, but if you just your eye goes down from this panel to this panel, you can see droplets growing as this is being heated by the temperature, by the sunlight. Okay? This means that the challenge of trapping water from low humidity is solved. Okay, it is not an exaggeration, it is based on data in the lab. And now this experiment shows for the first time that you can take a primitive device based on this material, harvest the water from the atmosphere, and get droplets. So this is just the data that shows you when water goes into the material, it heats up. It's an exothermic reaction. Then it equilibrates. And then as you expose, this is my arrow, when it's exposed to the sun, the temperature heats up. Okay? And this is the behavior of the collection versus the temperature. And so in just this experiment, you can harvest basically 240 milliliter per or 0.24 kilogram of water per kilogram of material. Okay, it doesn't look like a lot. Okay, but remember, this is no energy input, just sunlight. You're out in the desert, there's absolutely nothing, and you have 1 kilo, and you get out a can of Coke of water. Okay, to me that is amazing, because you can have 1,000 kilos sitting there, like those tanks, water tanks. You can fill them up with the moth. It sits there. Now you can harvest 1,000 times a can of Coke. You're doing nothing. It's a day and night cycle. Better than that, for most of the world where there is electric or there is a solar, you're able to use a solar panel, you don't have to wait for the day and night cycle. You can pump air into the material, and then when the material is saturated, take it out. Okay? And so on and so forth. You repeat this, and based on the kinetics of our experiment, you can repeat this 15 times a day. Okay, for that experiment of 1 kilo. So our calculation is that you can deliver 100 liters of water every hour in a relative humidity of 30% using 1,000 kilos of moth. Okay, that's about the size of the average tank on top of a house. So this really gives me the idea that perhaps we could have houses in arid regions off the grid, and you can generate your own water for household use and for drinking. But also you can use it for agriculture. You can think of cartridges that would be stuck exposed on one side to the atmosphere, and a pipe that goes under the ground where it's cooler and constantly condensing water from the atmosphere. So where are we right now? We have the laboratory experiment worked out very well. We have the experiment outside the lab, and now we have scaled up, and I'm not showing anything here. We scaled it up to a kilogram quantity and tested it in Arizona. And all I can say is that it works. It works. And so I would say the experiment in Arizona taught us a lot about the device design. But the reason I am very excited about this is that the experiment, both in the laboratory and outside, works. The key element in this is the moth. And so the other great thing about this moth, not this particular one, but in MOF chemistry, is that I can move that edge to also 60% humidity and 80% humidity, which means that I can just put it in high humidity region, like next to the Gulf, and desalinate water. Okay? So I can shift that edge wherever I want it based on the way the pores are fashioned. So I think there are great things to come for water harvesting. So there are many other applications that we have and others have been, including medical applications that we have been using. Water capture, proton conductors for fuel cells, sensors, optoelectronic materials, luminescent material, drug carriers, a lot on heterogeneous catalysis, photocatalysis, electrocatalysis, electrical conductivity, gas storage, gas separation, gas capture. We have figured out a way of, let's say, twisting the will of nature to what we want, okay, which is designing materials on the molecular and atomic level. And that's not missed out on many companies who have a program. So finally, what I want to do in terms of I see here that I have 15 minutes. I just want to show you that the way I do science, that I always dream about something that no one can make, that it's not obvious how to make it. This is how MOF chemistry was created. Tomorrow I'll talk about KFAS and ZIFs, other classes of materials. But weaving is the oldest way of making fabric. It's still being used today. Nobody has figured out a way of doing this with molecules. Why would that be important? A lot of the structures that I showed you are porous, rigid, architecturally robust. But what about if I could make things that are of that type, but also flexible? The reason this tie is very sturdy is because it's made of fibers that when I bend or stretch, they slide. The fibers slide with respect to each other, but they are trapped mechanically. They are interlaced. So they never lose their vicinity, and therefore they will always go back. Okay, you can't do that with molecules. Nobody has figured out how to do that in molecules. So you have a system like this where you have fibers that are weaving or interlacing with other fibers. This is a woven fabric, but could we make it out of molecules? So I talked to many organic chemists about this, many chemists, and they said it's impossible. Why? Because they were thinking that you have to make the fiber and then throw all these fibers together to make this intricate and regularly arranged pattern. Well, I agree that that's impossible. But what has our chemistry changed? The building block approach to making material. It changed the way we think. Because now all I need is a fragment of this one. Okay? I need just one up and down, and then I link it up together. So to produce a woven structure without having to actually weave. Okay, so that's what we call reticular chemistry thinking. Now this becomes possible. You can now play with it, make a chain link fence or 3D helical weaving. So that's another thing, is that you don't go to a student and say, make me a woven fabric. They'll just laugh you out of town. They say, I want to get a PhD. Okay, I want a project that works. So, but if you tell a student, make this up and down complex, they immediately will say, no problem. And so she made this nice copper. We have a copper here that brings these two segments together. These are my up and down building unit. And she functionalized them with aldehydes and copolymerized it with the amine to make imine, and I'll talk more about this tomorrow in my lecture, to make imine, and that's the beginning of the fiber. So I colored them different so that this fiber is blue, another one is orange. And so you have something that looks like woven, but now I can take the copper out. If I add potassium cyanide to it, I completely remove the copper, or if I want the copper, I can also put it back into here, because the nitrogens determine exactly where the copper go. There is a registry there. So the material without the copper, this woven structure, is tenfold, has tenfold increase in elasticity compared to the one with copper. Okay, so the dream of making a porous material that preserves its porosity but is resilient and flexible becomes real. That means that I don't have to necessarily, I can manufacture things in many different forms that could do the water harvesting or the CO2 capture or many other applications, catalysis. Okay, this is a more organized way of presenting it. You can see the fibers interlacing in and out of each other. Well, I'm a blessed person. Everything I touch becomes great. I don't know why, but I am very blessed. And when you think about it, every structure, including the one at KFAS, the square grid, can be woven. Okay, every structure can be woven. Here's a Kagome lattice that physicists like very much, the structure. It can be woven from fibers. Okay, here's primitive cubic. This is the Asher drawing that I showed you. It can be woven. This is a structure of ice under the ocean where methane is trapped. It can be woven. If you have a fiber, we can weave whatever structure you can imagine. Okay, all you have to do is make sure you have the up and down and you control the angles between the up and down, and that's it. So here's one on the left with fiber, but also the other element of design, you could also weave things from rings, like chainmail. Okay, so for the very first time in the history of chemistry, we are able to make woven structure that adds above and beyond the porosity and the rigidity that we already have in MOFs. You can make braids. Okay, so today I just covered this. And the woven structures are really COFs, they're all organic. When you remove the copper, they're all organic. But tomorrow I'll tell you more about this, how we can use these COFs to turn carbon dioxide to fuels, and then these amazing ZIFs that are very important also for carbon capture. But this is what I've been saying all evening. We have invented a new way of thinking, a new way of doing chemistry, and that is not missed on a lot of the young people engaged in or hoping to do science around the world. So I would give sometimes lectures like this, and then a swarm of students come to me, and half of them, they want to come to my lab to do the chemistry. And I realized very quickly that it's going to be impossible to do. And this coincided with the first country to come to me to create a center was Vietnam. These are Vietnamese students. They had absolutely nothing. They didn't have labs. They just had the will to do chemistry. MOFs and COFs are really not very difficult to make. There are, I didn't mention, but there are about 40,000 MOFs known today. There are 1,000 groups around the world working in this area, in academia and industry. So what we did then is after Vietnam and a couple of other countries that we went into, we developed a model for how to succeed. The first was inclusivity, is that you want to be able to bring everybody in. Everybody that has the merit and the will to succeed can plug in. You need a mutual understanding. People need to be able, you need to be able to have a contract where we deliver something and you deliver something. You need accessibility. People have to have access to instrumentation and talent on both sides. Working from a position, this is very important. Everyone has something to offer. Berkeley offers certain things. The partnering country has strength in certain others, sometimes strength in providing problems that we've never thought about. Sometimes, whatever it is, there's a strength. So we like to say that both sides have to bring something to the table and something that they can do best, and it's always on equal basis. If there is no infrastructure for research, we work together with with the local governments and the local scientists to build one. You always, after a few years, you need a sustainability plan. You start thinking, well, how can this thing grow in the absence of the people who started it? And of course, funding is never the problem. Every country that has asked us to work with them has been able to find the funding. Even countries that you would think don't have money for research, once we partner with them, we help them write grants and together with them to get the funding. And of course, we keep the government engaged in terms of what we are doing so that we can capture opportunities as they arise. But the three things that I really believe in this, I don't need another paper. And I'm happy just doing what I'm doing. But really my interest is really providing opportunity for young scholars to plug into research and improve their lives. I believe in the resiliency of the individual, is that people are very tough, very sturdy, okay? If you challenge them, they jump. You just have to have the right opportunity in place. And science is transformational, meaning that you could have a situation where you don't think you can solve the problem, but by doing science, by discovering something, you could change that equation. You could become the world expert on it, okay, because of that discovery. That means that you are never necessarily always on top or always on the bottom, because science changes everything. And then the one-on-one unconditional giving. I find this to be very important. The one-on-one interaction, if you're a professor, your interaction with that student transforms that student. And that's the reason we've been very productive in the lab. Because I just have, in my own lab and in a lot of our interactions with partnering countries, we don't have lieutenants, okay? It's the professor talking directly to the student and helping the student directly. So we've been developing centers of excellence in each one of these countries. Each country has its own parameters, its own science that they want to develop, its own capacity building and there are many more that are in the pipeline that are engaged with us in discussions about what will be developed. So so far we've built a network of nodes, both centers, physical centers that students can plug in, and the dots here are affiliates. These are people that we know from various fields. With just one phone call, they can travel to a partnering country and give lectures, mentor students, and engage. You will be surprised that many of us are more than happy to give our expertise to young scholars. And so we have never failed in being able to take an expert we wanted in these dots, to take them and put them where we want them to engage with students. So this is the last slide I have. This is what our Berkeley Global Institute has been able to do. We have, just in the last 5 years, we have published 85 high impact papers. And that's not from my work at Berkeley, but this is the work that's going on in the partnering countries. Some of these papers have impact factors as high as 40. Okay. 15 plus workshops we have held in these places. 200 plus scholars mentored. This is one-on-one mentoring. These are people that I have, or my former students who've been mentored by me had direct impact on. 300 scholars participated in our programs locally at UCB, coming to UCB. And 1,000 plus scholars. So this is the beautiful thing. You start something, but then everybody's looking and everybody wants to participate, and they use this as an example. Okay, so there's a lot of secondary and tertiary effects. Okay, well, I usually don't conclude because the story will continue in future. This is the funding And of course, I want to acknowledge my capable students, and I want to acknowledge KFAS. Dr. Adnan, thank you for the invitation. It's a pleasure to meet members of KFAS, and thank you for coming.
Thank you very much.
Yeah, thank you.
I think we will have some time for questions, but before I open the floor for, do you have time to take some few questions?
It will be a pleasure.
Yeah. We have another engagement, but I think this is much more important than another engagement. But before I open the floor, how many of you are from Kuwait University? Raise your hand. Good. How many of you are from KISR, Kuwait Institute for Science? Not as many, but tomorrow Professor Yaghi will be both at Kuwait University and at KISR. So that will just, this is like a teaser. And tomorrow the real scientific exchange will take place at both places. We had the president of Kuwait University was with us. He said he will attend 15 minutes. He attended 1 hour and 10 minutes. So I'm happy with that. So first question, Dr. Hamid, you have the microphone. And I will try to be even.
Okay. Shukran, Dr. Yaghi.
Brief,
Thank you so much, Dr. Yaghi. It's really impressive, and we are learning a lot from you. I have two questions. The first question is that you haven't mentioned anything about the conductivity of this material, whether it could be used as a conductor or as an insulation material. And the second thing, you have not mentioned anything about the cost of the material. How much 1,000 kg will cost to produce 100 liter of water? Thank you so much.
Okay, thank you. Yes, there are a lot of things I have not mentioned because this is really a very, very big field, and it's just difficult to cover everything in one lecture. Concerning the first question about conductivity, we and others have made conductive frameworks. We made conductive COFs. There's a group at MIT that has recently reported conductive MOFs, and they're using them as supercapacitors to store charges. So there are strategies out there to make MOFs conductive. The MOFs I showed you tonight were not conductive, but there are ones that are based on caticolate linkers with mixed metal, with mixed redox oxidation state metals that can be that have been made and reported as being conductive. So that's a good question. The cost question is a big secret by BASF. Okay, but if the cost is a problem, BASF wouldn't be investing so much in MOFs. But let me just maybe try to answer this. The cost of the MOF is not the organic, but it's the metal. Okay, so to check the metal cost, you just have to go to Google and ask how much is a kilo of zinc, and that will tell you roughly how much the cost of the MOF is going to be. Zinc is cheap. Zinc is $5 a kilo. Copper is $25 a kilo. Zirconium is $160 a kilo. Okay, but the structure I showed you is zirconium, but we have structures right now that behave even better than the zirconium that are made from aluminum. Okay, and aluminum is dirt cheap. Another thing that I didn't discuss, some of you may be very uncomfortable drinking water out of a MOF because of the metal. We have tested the water, and there is absolutely not trace of metals at all or organic. So these are materials. The metal is really held by these chelations through strong bonds, and they are hydrolytically very stable.
I saw a bunch of students there. Are there any questions from the students out there? No questions from the students?
Adnan, I have a question just to follow on that point, please.
Who's that?
Anna Leila.
You're not a student, but go ahead.
I'm always a student. You make me write note to files every day, so I guess I have homework.
She's a highly paid student.
I would like to ask about the quality of the water, because what is it? Is it distilled water quality?
Yes.
Are there solubles in it?
No.
Nothing.
No, it's a distilled water. And those of you who work on water, it's very easy to mineralize it. So you just, there are packets that you drop into the tank. And
We are expert here.
yeah, yeah. So yeah, it's distilled.
I'm trying. Second
Keep in mind, by the way, let me just elaborate on that. Keep in mind that the MOF is nanoscopically porous. So the pores only admit water. But if there is something in the air other than water, nitrogen, it's not going to let it in. Okay? So it's a filter.
Salam.
Okay. Thank you, Dr. Yaghi. What an eye-opening lecture, really, for us. While understanding the stability of the MOF structure, I'm wondering if the temperature that is, when it is rising, it squeezes the fluids or the water, namely out of the pores. Wouldn't the pores be expanding also at the same scale? Therefore, maybe less efficient the system is?
That's the beauty of what we have done, is that the pores are rigid, and because the building units are these metal clusters, so they don't shear. They are, in fact, I didn't go through it, but if you look at one of these MOFs, MOF 5, you find that the linkers on either side of the multi-metallic unit, they are actually 90 degrees to each other. They are twisted just like you would do. So there are 6 of them, and each pair is twisted. And that's exactly what you do to build a structure, build a barn or a physical structure, so that the structure doesn't shear. So no, they don't show. Now there are some MOFs that others have made that show flexibility because of the way the multi-metallic units are arranged. So there are like an accordion. They could, yeah.
But the ones in Berkeley are very solid.
Yeah, that's I'm working on solid ones. Please. Yes.
Thank you. I have something about the PET surface area. It's very high, in fact, 2,900. Because I'm comparing.
What about the 10,000? That's even higher.
Exactly, yeah. And I'm comparing it with the nature. For example, dust. Here in Kuwait, we have the highest surface area maybe in the world. But so high because it's 10 meters square per gram. But here's 29 or 10,000, whatever. It's very high. In fact, it means contains angularity and cavities in this material.
Yes. Yes. So if I take a granule of sand, the outside surface is almost negligible compared to that same sand particle if I riddled it with holes on the nano level. Okay? So it might have, 5 meters square per gram surface area on the outside, but if I riddle it with holes, like I did with these MOFs, you will get 10,000 meters square per gram. That's the beauty of the internal surface area. Yeah.
Please, in the middle, and then Tahir. Middle.
But by the way, I want to go back to the rigidity because I don't want people to go away thinking that that's just for fun. If you have a rigid structure, you can, like in petroleum refining, you can separate the linear from the branched. But if it flexes, then you don't have selectivity. So that's another reason for the rigidity. Yeah.
Please.
Yes, thanks. My question, I actually have 2. First one is, how does the system respond in a corrosive environment with, say, like a high concentration of ozone or sulfuric acid, sulfur dioxide, because of the polymers? And the second is, how do you see the current scientific environment in the States, given the current status of our enlightened leadership?
So there are some MOFs, I didn't put them in here, but there's a MOF 808 that we sulfate to make super acids. Okay, so you can replace certain components in the pores with sulfate, and then with the presence of water, you can make super acids, and they're very, very stable. Okay, now there are some MOFs, if you expose them to H2S, they will react to make, the zinc ones will react to make zinc sulfide. So it just, not all MOFs are created equal. Okay, so it just depends on what you want to do. I'm a strong believer in there are opportunities if you want to find them. So enlightened leadership or not so enlightened leadership, science still moves on, and science will always be needed by society. So I'm not as discouraged in the long term.
Yeah. Professor Yaghi in my office was telling me a secret about what they're doing in Berkeley with these MOFs. They're developing MOFs that capture undesirable politicians. Please, we have Dr. Tahir first, because, yeah.
Yes, you mentioned that when you started this and discovered MOBs, students said that we should not tell everything in our paper so that nobody will repeat the work. In hindsight, of course, now we will see that without divulging this explosion of work would not have happened. Now, in many cases in science, people are really think very much about intellectual property, and they start to say that we should patent this, and also the organization or institution will encourage you to patent it so that it will be rewarding in the long run. In terms of, so what do you think about this, about intellectual property and patenting and this?
We patented the original compositions of MOFs. There is encyclopedic patents on MOFs that we did very early on, including the fact that since we know, like the square grid I was referring to, we know all those topologies that people potentially could make MOFs out of. We claim those as well. But the key is that was not first in my mind. The first thing in my mind was, I made a discovery, it's exciting, let's report it to the world. And ethics demands that you report procedure as you did it, reproducibly, right? You reproduce your science. And then everything beyond that is not my concern, right? But we know that in science, if you don't patent, then you don't get industrial money. So you need if you think you have an important discovery, you should patent it. But usually, I submit the patent disclosure, and it does not delay my publication of the work. As long as you have a patent disclosure filed, it's fine. Yeah.
We talked about it during reception at lunch, and we are going to claim the patent about the KFAS because I think it was designed before you. Please.
Thank you, Professor Omar, for your information and for your time. I have any technology, it has two things to survive, economics and environment. So you didn't give an answer for mineralizing this water because you will produce distilled water. To use this water in agriculture, for a human, for drinking, should be mineralized. So this is the cost also. So the cost is very important. It shouldn't be a secret, I think. The second thing, did you assess the environmental impact of this? Because you are sucking oxygen and hydrogen from the environment. So what is the effect on the oxygen level in the surrounding environment of this device? Thank you.
I think mineralizing distilled water is very easy. That's something that's not, and it's not expensive. That's just salt, so it's very cheap. The question about the environmental impact of sucking water out of the air, you mean? There's a lot of water in the air, and the nice thing is that it moves. It's not, if I suck up the water out of Kuwait City atmosphere, it doesn't stay dry. It moves. So, and thankfully, water is recyclable, so it evaporates. So I think if you cover the whole of Kuwait with farms of that are sucking water out of the air, maybe you get microclimate changes. But that's not how I think. I'm a scientist, and the first thing I think about is first addressing the problem, Okay, now we are prototyping it. We are learning about different things. That doesn't mean that we ignore the cost. But how can I talk about the cost? How can I talk about all these things when we have not built the system that is ultimately going to be deployed? So there's a lot of stuff we have to do between now and talking about cost. But the cost of MOF is not a problem. The rest of the stuff is already there. The material is already there. It's the cost, if there's any cost, it would be the MOF, and it's not a problem.
Last question.
Thank you, Professor, for your nice talk. I'm interested in the pore size. You haven't mentioned the pore size. Is it like mesoporous or macro?
So the pore size of most of the structures I showed you varies between half a nanometer all the way. The pore that you produce from that long link is about 10 nanometer. So it's very easy to make things in that range. And you can control them on a minute scale, actually, depending on the length of the linker, and the kind of structure.
The second question, please, it's about the stability, the mechanical stability, because it's a porous, and the thermal stability. If you can give me
The thermal stability of MOFs is in the range of 300 to 400 degrees C. Just think about it. They're made from carbon-carbon bonds, carbon-oxygen bond, and metal oxide type of bond. And all of those are at least 350 kilojoules per mole, 370 kilojoules per mole. So they're very stable thermally. Chemically, I showed examples where we are stuffing water in the MOF. I mentioned the example of boiling them in strong acid, H2SO4, to make the super acidic MOFs.
Mechanically.
Mechanical stability. I know that to make the the natural gas tank for those automobiles, you have to press the pellets and do many things.
Exactly.
Those usually preserve their porosity. There may be a variation of 10%. Yeah. So at those pressures, they are mechanically stable. Yeah.
So can I have one last question?
You can, because you were not the last, the penultimate. The ultimate will be Dr. Nourieh.
There's also a student there.
Is there a question from a student? Okay, I will give you the floor after the student, please. Because I think it's more interesting to hear the students.
First of all, thank you very much, Professor.
You're from Kuwait University?
The lecture was very enlightening. I just have something, if you could answer, just to understand. So right now you can actually design or make a structure for the MOFs so that it fills anything or any molecule you desire, or right now it's just like simple structures and simple compounds?
No, everything you can think of, from oxygen, nitrogen, hydrogen, methane, water, CO2, methanol, benzene. I didn't talk about this, but we can put drug molecules, very complex molecules, proteins. We put in GFP in there. We put in vitamin B12. Almost anything you can think of any complexity. The only limitation is size, right? We can put proteins, but not very large proteins yet. But in terms of molecules, it's just a wide variety. And the reason for that, and ions, because you can functionalize the interior to suit whatever you need. And I didn't do all of that in my group, but I did some of it. But the community is doing that, and it's being reported. Yeah.
Second question, there was another student. That's it?
He has a follow-up.
You had a follow-up? Please go ahead.
So right now, just it's an add-on of harvesting water. You can also right now not harvest, but like use the MOFs as a purifier.
Yes,
for air and other things.
Yes. Well, you can use it to also clean water, organics from water. That's an application that's already being used. Yeah. No, I didn't. I only talked about 0.0001% of what's out there. Right, this is a huge field. Yeah.
Professor.
Professor Omar, you started with basic chemistry. I mean, as a basic scientist. Are you still doing the chemistry work or just the application of the metal organic framework?
Yeah. I don't really distinguish between the two, but the way we started this research was more about trying to understand how do you design materials, how do you make materials by design. So it was more of an intellectual challenge. We didn't have a specific problem to solve necessarily for society, as I mentioned. I think that that's a very meaningful way of doing science for chemists. Okay. If I start with a target application, carbon capture, I am very sure we would not have invented MOFs and COFs. We would have used some other material. So while you can, as an engineer would, define a problem and try to find a solution, you ultimately have to ask, well, how does it work? How can I make that quantum leap? Well, you're not going to make that quantum leap unless you go dig down into the basic science. And so my favorite way of doing science is to do the basic science first and then build it up. Okay, but everything is working against that nowadays, from funding agencies to, so we have to be very clever on how we present the problem, right? So yeah.
How long it took you? Please.
Is it the function of the metal atoms or the organic functional groups around which affect the rate or the amount of the storage efficiency?
It depends. For hydrogen, when you expose the metal sites, you get more hydrogen binding into the MOF strongly, and that's what you need. You need that higher binding energy to be able to store at room temperature. In the case of superacid, you're binding directly into the metal site. In some cases, it's the organic. And the carbon capture, we modified the organic to capture the CO2. So it just depends on your application. It depends on the material, depends on many different things. So both of them can be utilized. It just depends on the application.
So I have a question. In your presentation, you showed that professor or somebody who told you, what can you do with this? How many years it took you to get to that point?
Well, I mean,
I have a reason why I'm asking.
Yeah, I mean, I don't think my answer is very reliable because I was not aiming for helping society. So.
But that's an important.
But I would say that it took us for the first carbon capture experiment. I would say, with consciously trying to pursue something, it didn't take very long. It took a couple of years.
No, but from the time you started your work, from assistant professor until you reached that point with your research.
It could be about 6 years.
Okay. Well, that tells you that you have to invest in basic research before you get applied research.
You do. If you don't invest in basic research, you will not have any legs to stand on. You can build fancy stuff. At the end of the day, you have to go back to the basic science, not just because you want to understand how things work, for innovations, for new innovations, because science, a discovery can change everything, right? Yeah.
We will have Professor Yaghi again with us on the 13th of December when he is awarded the Kuwait Prize. So we'll have another lecture. Hopefully you can attract other people. Maybe you can have MOFs and COFs and POFs and whatever it is. So thank you very much. It's been really a delight.
Thank you.